now we're going to transition into our last panel. And sorry, see here. So this panel is really focused on the concept of grid integrated or grid efficient buildings that are integrated, efficient buildings that are integrated with the grid. The historically SB 2030 is sort of structured on the idea that we inherited from the Architecture 2030 program that really focused on, and this is true of many aspects of sort of the green building movement and incorporating energy, that focused on kind of the end goal being the net zero building on site. So you're making the building efficient, and then you're focused on being net zero and doing that as much as possible, or actually not more than as much as possible, doing that with renewable energy on the building site. In fact, before we revised some of the requirements of adding renewables that allowed scale jumping that Pat just went through, where if you couldn't put it on the building, you could jump to the site, you could jump to the campus, you could do those kinds of things. We actually didn't even allow that kind of scale jumping. It had to be kind of it feels weird to say this now, but the traditional version of net zero with efficient building. The renewables had to be, on the roof, on the site of that building as our approach to net zero. And we still have that, we expand the scale somewhat in our approach to jumping scales and the hierarchy that Pat introduced. But this panel starts to kind of raise the question and start to think about, as we create very, very efficient buildings that are at this point of, and now SB 2030 buildings, as we heard in the previous panel, they're at the point of every project is at the cost-effective limit of energy efficiency. They also have now, with our more up-to-date requirements, they are net zero ready, even if they're not doing renewables on the roof, on the site. They're structuring for them to happen in the future. They're putting conduits for them to happen in the future. So they're at the, very efficient, energy efficient buildings. They're net zero ready. So how do we think about in the future, as these are long-term assets for the owners who are building these projects, as they go through their life and maybe add renewables in the future, how will those interact with the grid? And we also know that, some net zero buildings might be generating energy with their solar at times when the grid might not need that solar. So are there other ways that we can think about buildings that they can not only be efficient, but also have distributed resources for the grid, like their efficiency, like efficient envelopes, like renewable, like solar panels, or other items in the building that can be real distributed resources for the grid. And we need to think about in the future how they kind of interact or be smart buildings that interplay with the grid. As we, they're adding storage of some sort. Maybe they're adding battery storage. And all of these strategies and technologies are part of thinking about the built environment as we make it more efficient. And then also, as we get higher levels of renewables in the grid, do we have the strategies in these buildings so that the grid is still reliable, still cost effective, and still providing energy for the needs that we have in the built environment. So that's the focus of the panel. Our panelists, and I'll let them tell more about themselves as they go into each of their presentations. But our panelists today are Lester Shen from the Center for Energy and Environment. He's going to do an overview of what is this topic, kind of to give us some context. Andre Gouin from Xcel Energy. He's going to talk about grid efficient and interactive buildings from the utilities perspective. And then we have Greenhalgh from Honeywell, who's going to talk about storage and other technologies that can be integrated into these buildings. And then we have Scott Schuetter from Slipstream, who's going to talk about examples of these buildings, how they fit into neighborhood context, grid context, and then the future directions of research. So with that, I'll hand it off to Lester, and feel free, and please, when we get to the end, we hopefully will have 15-20 minutes for Q&A and discussion, but feel free to ask questions in the Q&A function of the webinar as we go. So with that, I'll hand it over to Lester and give it a go with sharing your screen, and hopefully this works. There we go, it works.
Great.
Thanks,
Richard. Yeah, so I'm going to give kind of an overview of grid interactive efficient buildings, also known as GEBs. It's something that is going to become more and more talked about as we move ahead, looking at going towards net zero, dealing with climate change, going towards a carbon-free energy sources. And it's a priority that the Department of Energy is currently putting a lot of funding into, and I think it's an emphasis that we will be moving towards, not just with buildings, but it's a more of a systems approach in terms of how all of our energy uses and interact with how energy or power is generated, and how we can sync everything. To understand GEBs, I want to start with the Internet of Things. The Internet of Things has been very popular and fashionable, and probably has been somewhat lacking in the promise that it's been touted to give us. But you may recognize some of these smart devices, and many of you may have them in your homes. And the idea is that they were to save energy, and they do help us save energy, and they can make our homes smart, but that doesn't mean our homes have a brain. They help to automate the home, but more importantly, they create new interactions, which we're finding makes our occupancy of these homes maybe more convenient. You know, you can now interact with the devices in your home with a smartphone. You can do it over voice with Alexa or Google Assistant. You can now control not only the heating and cooling, but your lights, your plug loads, and even look at security. And the nice thing that it's starting to show us is that the interactions that we have with our homes and our buildings aren't just isolated to us occupying or being inside the house. It now lets us interact when we're outside the house through our smartphones, where maybe we're out and we say, oh, we forgot to turn the lights off, and we can check on our smartphone what lights are on or off and turn them off. We can adjust the temperature. And so it's something that is allowing us an ability to interact with buildings in a much greater way. And that's what I think we should look at smart buildings as, is not just kind of the brains, but the new interactions that they permit us. And on the residential side, I think there are the energy benefits. I think a lot of the benefits from smart technologies are out of convenience and probably security. And I think at this point, the greatest advantages of Internet of Things we're seeing in the commercial market. And we're seeing intelligent buildings become a more important piece of how we manage and operate commercial buildings. And we're seeing how building automation is now expanding. And instead of just lights or the building automation system dealing with heating and cooling, we can look at energy management, we can do monitoring, we can look at dashboards to control and look for not just operations, but maintenance and discern where the equipment is operating properly. And then we're starting to integrate not just the building operations, but information technology and the operation technologies, telecommunications, into this kind of unified approach to how we look at buildings. And this is where kind of the Internet of Things are leading, and this is where the potential for smart technologies and intelligence in buildings is going. And so what does that mean? Well, by better operations and maintenance, it can help us increase the efficiency of how we operate buildings. So this curve shows what the typical building energy load for a commercial building is. And obviously, efficiency is something that we want to attain. We want to lower the costs, we want to lower our carbon footprint, and just within the building, that's really important. But the story isn't that simple, because when you bring all of the buildings together, they create a real demand on what power we need. And so obviously buildings are connected to the grid, and we require power from our power plants to help us run the buildings, and we use energy. And so we need to look at what the interaction is between, or how the grid and the building interact, and what the impact of the buildings are on the grid and on our energy demand. Now, currently, our energy mix, our primary energy mix, is from fossil fuels and nuclear. And much of the energy there, I think we can say, is we can look at those energy fuels as kind of stored energy. And so when we need the energy, we have power plants to release the energy that's stored in these fuels, and they provide energy that we can then consume. And so we have a load or an end use, and we rely on the grid to help provide the energy we need, or the power. Now, as we move towards renewables, we are starting to look at energy sources that maybe are obviously non-carbon, but they are more intermittent. And how does that impact how power is provided to us? This is known as the duck curve. And this is something that became an issue in California when solar energy was becoming a more prominent energy source on in the grid. And during the daylight hours, more energy was provided from solar, and as a result, less energy was demanded from the grid. And that's great. It reduces the amount of fossil fuels that we end up burning. On the other hand, what it does is it has an impact on our energy generation, in that as more and more solar is generated during the daylight hours, we end up with a surplus of energy coming from our power plants. And then as the sun goes down, demand for energy from the power plants goes up. And what that has done is it requires us to look at how we can manage the grid so that we can have a more, let's see if I can go back, there we go. What we want to do is see how we can get a more flattened demand so that we can more easily generate the power that's needed. And that, whoops, sorry about that. mouse is too sensitive. And so what that's causing is it's bringing about the idea of how can we make our demand, our load profiles be more flexible so that we can stop or reduce the variation in load that we're causing on the, or demand that we're causing on the grid. And that's where the ability to use intelligent buildings, smart technologies to interact between the building and the grid allows us more flexibility. And by demand flexibility, we're looking at ways that we can flatten this demand curve. Obviously, efficiency brings the total demand down. Load shedding is a way that during peak hours, how can we reduce the peak demand in the afternoons? And maybe there's some battery storage that can do that. Load shifting is another way where we can take some of the load from, say, the afternoon and shift it into the morning hours. And we're seeing some of that with electric hot water heaters that does some thermal storage for us. And then there's different modulations that might occur that are on the order time frame of seconds and seconds that we want to reduce the modulations that cause disruptions and stress on the grid. And so that is what we're looking for in terms of how we can look at the demand that buildings generate, what their impact is on the grid, and what these interactions or what the technologies that are coming to the market can help us reduce the those disruptions to the grid or possible disruptions to give us more reliable energy. And so that's what we call grid interactive energy efficient buildings. And basically it's the use of smart technologies combined with the distributed energy resources that are on the site. That includes generation, say PV, that could include battery storage. Electric vehicles are another DER that allows us to provide some demand flexibility in the buildings, and using those by interacting with the grid to optimize costs, grid services, and also satisfy the needs of the occupants. And then this is a graph or a figure showing how a grid interactive efficient building, or GEB, would work. And you can see that all of the connected devices inside the building, at the meter, how the meter connects and communicates with the grid, and then the building automation system, which then can help regulate how the energy demand of the building can be managed. And then the goal would be obviously reducing the load through efficiency, using efficiency and also generation and storage to make up for any gaps, and then eventually to hopefully shed and shift the load so that the power load or the energy demand of the building is now flattened. And the main characteristics of a GEB are that they're efficient, they're connected through two-way communication. Again, these are the interactions we're talking about. They're smart, so we need sensors, we need controllers that we can sense how the building is operating and then manage and control the use, maintaining the comfort for the occupants as well as supporting the productivity, and then being able to provide flexible loads. And this is basically how the building fits in with the grid in that it not only communicates with the grid, but these buildings will also be able to communicate with each other as well as the distributed energy sources to create the flexible loads that will be needed for our future energy mixes. Okay.
Great, thanks, Lester. So now we'll hear from Andre for the utility perspective on GEV. And Andre, there you go.
Button.
Yep.
Thanks, Richard, and thanks for having me on the panel this afternoon. I'm going to talk a little bit about how what is happening at Xcel Energy is driving the need for these grid interactive efficient buildings. And I am attempting to share.
There you go. It looks like it's working, Andre. Yep.
All right. So I'm a business technology consultant in Xcel Energy's Strategic Partners and Ventures group. And through that role, I get to work on a lot of different projects from electric vehicles to some of our carbon-free initiatives to some of our battery and microgrid projects. There we go. It wasn't advancing. So as most of you probably know, Xcel Energy, we're an investor-owned utility operating in 8 states. We serve roughly 3.7 million electric customers, 2.1 million gas customers, and are nationally recognized for our wind energy and energy efficiency programs. And I hope that everybody is aware of our comprehensive clean energy strategy that we plan on being 100% carbon-free electricity providers by 2050. We have plans to have net zero of natural gas emissions by 2050 and are enabling 1.5 million electric vehicles across our service territories by 2030. Kind of focusing on the electric side, as Lester was talking about, we determine the requirements of our system through what we call our resource plan. In Minnesota, our resource plan is our pathway to achieving 85% carbon reductions by 2030. And we plan on making this happen by first retiring coal plants and then adding a significant amount of renewables. So that would be all forms of solar, from utility scale solar to distributed solar through some of the programs that Crystal touched on earlier in the day. We want to extend our nuclear operations for that carbon-free resource. And then we kind of balance things by having dispatchable natural gas generation that will balance the loads while running a minimum amount of time possible. But this grid mix is really changing with the addition of these intermittent resources, as Lester was mentioning. So what tools does Xcel Energy have to help manage the grid? I'm going to touch on 3 of them. One is our advanced grid programs. Another one is our demand response programs. And a third that we're starting to look at is battery storage and microgrids. So first, our advanced grid programs. Really, this is a foundational layer. It helps with that communications piece. We don't know what's going on at the outskirts or the grid edge unless we have the ability to communicate. That starts with having a centralized software system that can collect and analyze data from remote devices. The remote devices can correct faults and restore power quickly. We can use them to optimize the amount of voltage we're supplying on our system. And then we are rolling out our advanced metering infrastructure, or our smart meters, across our service territory, which will provide near real-time data to all of our from all of our customer points. And all that is connected through a network, our field area network. And so this foundational layer, as I said, pulls together all this data so we can better understand in real time the needs of the grid and how we need to manage loads to support this intermittent renewable sources of generation that are coming online. Another tool is our demand response programs. And demand response programs are really important because I feel they're the mechanism for which we incentivize customers to change their behavior, change their loads. So as Lester was saying, it with all the new technology and Internet of Things, you can, buildings are able to manage their loads much more accurately and in real time. But why should they? What's in it for them type of thing? Well, the demand response programs offer incentives to customers to do just that. This is a list of our current portfolio of programs. You can see we have nearly 950 megawatts of dispatchable DR, and that covers from our large C&I customers, commercial industrial customers, down to our residential customers with devices like our Saver switch, which cycles air conditioning loads. These are all based on kind of that traditional utility load profile where we have our peak days are typically in the middle of the summer. Think of that hot summer day when everybody's air conditioning is going on, and then we'll call a demand response event to cycle off those air conditioners and other commercial and industrial loads to really shade that peak. But that's all well and good with sort of the traditional electric load profile, but as things change, as more loads are electrified, our load starts to shift more to a winter peaking utility. Shutting off air conditioners is not going to help much if we're peaking in the winter. So we are looking at additional types of demand response programs, programs that offer us more of additional flexibility. So things like a peak flex credit, which will incentivize customers to provide us resources at different times. We're looking at pilots around commercial thermal energy storage. And then a real growing load on our system is electric vehicles. And we want to come up with programs that help us manage that and get the people charging when it's most beneficial to the grid or not detrimental to the grid. And the last tool I'll touch on is battery energy storage and microgrids. In Colorado back in 2016, we rolled out the first battery storage microgrid in the state. And we did so to demonstrate certain value propositions that battery storage can provide. I won't steal too much of our next speaker, Dave's thunder here, but some of the value propositions that we can get from battery storage are things like integrating a high penetration of PV, kind of doing that shifting of load that Lester mentioned in his presentation. We can reduce system peak by dispatching the batteries during those hot summer days, energy arbitrage, and even frequency regulation, getting down to the sub-cycle use of the battery to control the system frequency. And then an additional benefit is on the customer side. We wanted to show how we could create added resilience for customers by allowing these battery storage systems to provide backup power. The picture here sort of demonstrates or shows all the components that are necessary to kind of go into the microgrid. You need a generation asset, you need the load itself, which buildings are you controlling, you need the control center and the software management system to kind of pull everything together. And like this slide because it kind of shows you the scale of what one of these microgrid projects looks like. We partnered with Panasonic and put a microgrid in at their facility. So it's almost really a nanogrid in that it backs up a single facility, Panasonic's building. Off to the left, you can see a carport PV system that's part of the microgrid. We support Panasonic's 100,000 square foot warehouse facility. And then on the right-hand side, the blue box is our islanding switch, which isolates the facility and the generation assets from the rest of the grid during microgrid mode. And the storage assets are the white battery storage containers. So this project was really successful. We had a successful demonstration over a 3-year period. And now we're taking the learnings from this program and are proposing to do a similar project up in Minneapolis. We earlier, or last year, I should say, we put out an application to look for interested parties that would like to be part of our Resilient Minneapolis program. And the idea behind this is that we would just deploy battery storage projects that would provide grid benefits, and then they could also support the host site by being a resilience asset. Think of community centers where in times of emergency, storms or something of that nature, and there was a area-wide power outage, then those facilities could be resilient by having this backup storage system. So we did select 3 sites, and they're in or adjacent to Minneapolis's green zones. We filed those back in November of 2021, and we're waiting on a commission ruling on whether we can proceed with those, and that's expected by June of this year. And with that, I can cue it up or hand it over to Dave to give us some more information about battery storage.
Great, thanks, Andre. And Andre, as Dave is kind of getting his presentation up and running, one question I had, you mentioned a little bit the possibility of winter peaking in the Xcel grid, which is a new quality. So what are some of the qualities you're seeing as you're seeing more efficient buildings, more distributed solar and other resources and other, how, like high level, what are some of the ways you see the grid profile changing?
Yeah, I think the main thing that would drive that winter peaking is electrification of heating loads. As people are trying to reduce the amount of natural gas they're using, find alternatives for natural gas like air source heat pumps or ground source heat pumps. Our gas load goes down, but our electric demand will go up as buildings become more energy efficient in the summer, better insulation, the larger use of distributed energy resources like rooftop PV systems, which help drive down those buildings' summer peak demand. Then that's going to be replaced by the electrification loads that make up for the heating in the winter.
Great, thank you. Okay, Dave, go ahead.
All right, thanks so much for having me. Appreciate the time and the opportunity. My name is Dave Greenhalgh. I'm the Director of Sales for Honeywell's Energy Storage Solutions business. And so I'm gonna probably have a little bit different slant here this morning, or I guess this afternoon, sorry. I'm gonna talk a little bit future, and I'm just gonna do an overview of energy storage. Andre did a good job of really high level summarizing it up, or summarizing that, so I appreciate that. So let's just get into it. So just, you know, what Honeywell is doing in this space. from a corporation or corporate headquarters side of things, a little history, market, and benefits of energy storage, talk a little bit of technology and where that's going, some of the industry challenges, and then just a summary slide. So just like many discussions today, Honeywell is very much focused on a 2035 goal of carbon neutrality. And you can see that Honeywell has been very involved already since back in 2004, looking at CO2 reductions. We got a bunch of water reduction, and then sustainability projects into the multiple thousands since 2004. So kind of the saying of eating your own dog food. On the energy storage side of things, we definitely focused on looking at our plants and manufacturing facilities and taking dramatic steps. Last year, we closed 3 large PV and energy storage projects at our facilities in the US. We have another 5 on the books right now. And with the marketplace continuing to try to look at off-taker agreements to help with our RECs, which has been lots of talk about. So excited to see that Honeywell corporate and the organization is jumping on not only promoting in the sustainability space, but also investing in that area. So when we look at this, this is really what Honeywell does. As we're talking about buildings today, lots of you guys could be thinking, hey, I know these guys are the thermostat guys. And I would say that from this slide and from the work that we've done, we're a long ways away from the thermostats now, and really going all in on the sustainability solutions. Ones that I'd like us to really look at today that impact the story today would really be the renewable energy, which is really energy storage, and then lots of the applications around software and capabilities around controls, Lev, and then also the sustainability buildings, which is through our Honeywell Building Technology Group. And you can see they have a vast array of solutions that can really help optimize energy efficiency in the buildings. Just a little background. So really when we look at, at energy as a whole, we had centralized energy back up to about 2015, really conventional power generation. Then we had a big move from decentralization and decarbonization. And then a really key word, I think, as we go through the presentation is digitization to create this distributed energy. One of the problems that kind of created was really grid balancing, and a few of my co-presenters today have definitely talked about that, but that's really where we started seeing a lot of value in energy storage to help with that balancing. And you can see that there's 2 different flavors of that. And as we talk about short term, that's really the lithium ion and a few other chemistries that are out there. That's really around what Andre spoke to as far as peak shaving, frequency control, resiliency play within that. And then we start talking about the long duration, and this really creates a lot of interesting dynamics. Obviously, the long duration batteries need to prove themselves. And what I mean by long duration is really anything over 4 hours. You might hear the word flow batteries. But as we look at the grid and how we balance that, and we get out of just buildings and we start looking at maybe blocks, and we start looking at communities and potentially even cities, what does this really look like? And I think the long duration can definitely help with that challenge. So here's just a couple graphs just to put up some colors. And really what I wanted just to show is that energy storage, there's been lots of talk that, hey, this is just a fad, or this is going to be limited. And so the projections are huge. You can see a huge abundance of projects and growth, multiple gigawatts through the US. And so when we look at the energy capacity build, we're looking at the 325 gigawatts, which is just a big number to consider. We look at dollars spent, you can see there's been a huge jump from 2020 even to projected numbers for 2022. And then we still go up to about that $9 billion. So looking at some, again, reinforcing just that the energy storage build and energy continues to rise. Andre went over this pretty well, so I'll try to be quick here, but peak performance, improving energy bills, definitely when we look at different PPA types, we could really see that there's definitely cost savings. And as we're trying to pencil projects based on ROI, this is definitely the leading candidate. Another side is really just this carbon footprint reduction. And so when we look at a PV plus storage, type project, and we can really focus on the generators at site. Again, back to the resiliency play. If we can get energy storage with renewable energy really as your backup or your resiliency play away from the diesel generators, that can be a huge impact to the carbon footprint at buildings and at C&I sites. Demand response, we spoke to a little bit, in revenue stream. And so being able to have this backup power, being able to have a control system with software that can, through algorithms, really speak to what you should do with your excess energy, whether it's selling it back to the grid, whether it's charging your batteries or putting it to your process or your needs, is another way to really pencil and really have a hybrid, what we call BTM, so behind the meter, but really a hybrid solution where you have a few different revenue streams. This is really what the offering looks like from the technology side. On the left at the bottom, we really just have the lithium-ion, which is really standard, kind of like the Kleenex for tissue when you talk about battery technology. And then you have non-lithium-ion, or the long-term flow, long-duration batteries, again, back to the 4 hours plus. We start at the bottom, really the battery is the main piece, of course, and we have the battery management system. Then we move up to the container or enclosure, and we're starting to see some different types of technologies around panels for smaller kilowatt type. We're also looking at some cubes, which can control multiple different areas or sites, and that's newer technology that's just kind of on the horizon. So the standard 40-foot container and having a multitude of these, I think, is where we're kind of at today, but I'm really excited to see what happens over the next 3 to 5 years in what these solutions really turn out to. After the container side and the safety system inside, you start having the HVAC and just the whole control side with the fire detection, and then the controller, whether that be an RTU or PLC. And then you get up to the really operator side of things of the software, where you have the SCADA system, if you have multiple solutions or multiple containers, sorry, then the asset management, the fleet management, and then your VPP, which really goes back to that hybrid solution where the virtual power plant enables trading back to the grid. And then, of course, you just have your O&M as far as your energy performance contracts. That's what we call them, where you get some asset-backed KPI guarantees. You can also just have a long-term service agreement. When I went back to digitization, I would say that this is probably what we've seen over the last couple of years as far as that next step. And Andre also mentioned this, but really when we get to thinking, what's the future look like, and how do we not just talk about single buildings or just a couple buildings next to each other? How do we really get to this community and this distributed assets combination, and how do we really just manage this kind of fleet of assets? And so remote operating centers are definitely not new into the industrial space, and we're really starting to see this come across into the renewable energy side, in combination of not just the energy storage side, but also bringing in the solar PV and the wind assets as well. So when we think about buildings, these remote operating centers could tie into the building management side. And then you could really customize these different dashboards for KPIs against different levels of the organization or of ownership. When we talk about batteries for a second, with COVID coming around, with supply chain challenges and then inflation, we're seeing major increases, which is backwards to where the trend was the last 4 or 5 years for batteries. This graph really just shows that there's some different chemistries around short duration batteries that are on the horizon and really starting to make some waves. And what this is in my opinion, is a really good sign as gigafactories continue to get built, more supply, or that supply chain curve will change. And with competition drives prices down with supply chain as well. And we can really see some advantageous pricing on the horizon once we get past this blip that we're in right now. Some different just challenges. So some of the main challenges we've talked about, a lot of the speakers today, grid reliability, resiliency is a play. Energy storage can definitely help with that, along with the control solution, decarbonizing gas and reducing emissions. rising electricity bills, just managing new and existing distributed assets, which I just showed through the remote operations center. And then EV charging, we spoke to at length today, and then just grid constraints. And so energy storage can definitely build that on both the consumer and the provider on those sides. So where I think we want to go from a building management side of things is really just these projects are relatively new. I think that we can still see improved design. We're starting to see more and more financing, but I still think our governments can support us. I think from a knowledge side of project management and efficiency in implementation, I think the market or industry in partnership with the universities can create some programs around improving and supporting our project managers and just education. I think our testing and commissioning, although improving, still has a way to go. And then, of course, the measurement and verification of these elements has some way to go. And I think together we can definitely make those improvements. In summary, I just really think that energy management, including energy storage, along with remote operations, can really take a big step and a big leap into the future of achieving sustainability goals across the planet. So thank you very much for your time and appreciate it. I'll hand it back to Richard.
Thanks, Dave. Great. Well, now we're going to go to Scott Schuetter from Slipstream. And Dave, if you can stop sharing, and then Scott can get in here.
Okay.
I might be able to take it.
You might be able to take over too. There you go.
Yeah.
You got it.
Yeah. Yeah, so that's working. You can hear me. You can
Yep.
see my screen, all that.
Yep, you're good, Scott.
Okay, great. So yeah, kind of coming in here at the tail end, I realized that it's maybe been kind of a long day, and I'm hoping not to bore you further and maybe can engage you a little bit more by just starting off real quick and just wondering, to the extent to which any of you have any experience with these technologies, whether it's a battery or demand response program. I guess I can't really monitor the chat too much, but it would be interesting to know, at this point, if anybody is aware of things that are going on in this realm to date, because it is a pretty nascent, it's a pretty new field. So then to kind of transition from the previous speakers who all did a great job of kind of teeing up the topic and different perspectives from utilities and manufacturers. What I was hoping to chat about today is kind of what is it going on in the GEB space, some specific examples, and maybe some of the things that are coming down the pipe in terms of future research. So I'm Scott Schuetter. I'm a research engineer with Slipstream. We're nonprofit, operate mostly in the Midwest and definitely in Minnesota. So maybe you've heard of us. Most of our research is around emerging energy efficient technologies, which are very in line with a lot of what your previous speakers in different sessions were discussing. Recently, we've transitioned a part of our work into the GEB space, and what we're seeing in terms of current status is that it's early. There's a few GEB vendors on the software side, others on the hardware side. Their products are developing dynamically and quickly, as evidenced in part by the previous speakers, charts of capacity, installed battery capacity over the next several days and several years into decades. That's great to see. But it's going to take time to really reach scale, in part because there's a lot of stakeholders involved. To make GEB is really a whole systems approach, which integrates the utility, the building, and every stakeholder involved in the complete supply chain. That's utilities, that's integrators, that's manufacturers and contractors. And to get them all kind of on board and pulling in the same direction will take time. Kind of the current focus of development is in terms of system integration. So, you saw Andre speak to the microgrid and kind of getting all those systems to talk. You also saw the holistic approach as well, from batteries and pulling in other systems, and really getting further development both on just getting those systems integrated and communicating, but then also kind of optimizing the control of how they all are operating, which traditionally those systems are all standalone and don't communicate, but in the future they will, kind of back to Lester's point around kind of the smart buildings approach. The key for scalability is really defining the value for the end user or the building owner. So what are they getting out of it? And Andre alluded to that with respect to automated demand response programs and incentivizing participation in those. There's also, utility rate structure design elements and real-time pricing that can incentivize and allow the building owner to capture value from providing grid flexibility. So the key question maybe is how do we create this integrated and cost-effective GEB solution? It's got to be easy to use and it's got to benefit everybody involved. So that's kind of the long-term vision there. Here at Slipstream, we've done a variety of things in this space over the last maybe 2 years. The first was using our own building as a test bed. We knew this is a dynamic space. We knew it was pretty complicated, so we wanted to get our hands dirty and our feet wet, or by using our own building as kind of a guinea pig. We've implemented integration of a variety of our building systems, PV, HVAC, our submeterings, and even a little bit of our plug loads. We've done some pretty simple grid flexibility tests around load shedding and shifting on our building, and we're hoping to do more in the future. Here's just a picture of our building. It's here in Madison, Wisconsin. It's pretty typical office, built 13, 14 years ago now. Mid-size, typical operating schedule. HVAC system was nice at the time. It's a little dated now. It's a VAV. It's got an ERV on it, some boilers, backnet protocols on the BAS. Kind of pointing out our utility rate structure in that it's fairly typical, pretty straightforward, dollars per kWh, a pretty low demand charge in order to make grid flexibility, viable from demand reduction. It helps to have a high demand charge, so you can capture more value. But that is what we got right now. And our natural gas costs are less important because we're really flexing the electrical side of things, but just pointing out that I don't know about you all, but our natural gas prices have increased dramatically over the last 6 to 9 months. I think they've gone up like 50% on a dollars per therm basis. And then, we played around. We sent ourselves an automated demand response signal. Our systems grabbed it, saw it, and responded. On the right, you can see our basically our air handling unit dropping its power consumption roughly in half due to staging the compressors off and staging the fan down. So we were able to prove to ourselves, like, start to finish, this is how you do some grid flexibility. And that was a really useful learning curve. Got us up the learning curve a lot on how complicated and what the kind of sticking points were, barriers to implementation. We've also, since done some work with a variety of organizations, mostly the federal government at this point. This slide outlines our work supporting the General Service Administration which is often called like the landlord for the federal government. They own and operate, I don't know, like 1 billion square feet in the US of federal buildings. This one is a courthouse in Las Vegas, Nevada, a little bigger. It has boilers, similar air handling units, similar VAVs, boilers as well, but it's big enough to have chillers and cooling towers associated with that. And their rate structure is more complicated than than Slipstream's rate structure. But maybe I can point out the key thing is this higher demand charge, whereas ours was $3 a kW, theirs is closer to 13 during the summer on peak. And an interesting side note, to Andre's point about the utility scaled peak demand shifting from summer afternoons to winter, maybe mornings, due to electrification. What this utility is seeing is actually at least a near-term shift from kind of the 2 to 5 p.m. range during summer to the 5 to 8 p.m. range during the summer because of that penetration of solar resources on their grid, not unlike the duck curve that Lester showed earlier. So their grid-wide peak has gone down during the day due to that solar production, but as the sun goes down on hot days, they're setting the new peak then, which has some interesting questions around what systems are needed to provide flexibility in that range of time. So back to this demonstration, we're supporting prescriptive data, specifically their Nantum software platform. It has a variety of grid flexibility elements. The energy efficiency is provided in not too dissimilar ways from a lot of HVA control projects now. There's improved controls on the air handling startups and shutdowns, ramping ECMs as well will save chiller and fan energy. They are looking to get more into the grid flexibility space by doing some kind of at the bottom there, peak demand management. So looking at the interval data, this is the building's electric power consumption over a typical week during the summer. You can see it's really spiky, especially in the morning startup periods. And Nantum's going to use some machine learning algorithms to implement some control sequences to limit that peak events, and therefore limit the peak demand charges the utility or the building is seeing on a month-by-month basis. And then we're also planning to do some demand response. This Nevada utility has a demand response program, and we're planning to participate, receive an automated demand response signal, and then stage off equipment accordingly. This slide gives you a little better sense of what the Nantum software looks like to the end user, which is the facilities operating staff. This is for a demand response event. Coming up, there is some information about when it will occur. There's information about how much load is predicted to be shed. There's a forecast of what the building's load will look like and when the peak will occur, and then what the sequence of load shedding will correspondingly do. You kind of see that staged over here to the right. First, they're going to reset the supplier temperature, then they're going to reduce fans, then they're going to reduce chiller usage. So that's kind of what it looks like from the inside of the building side. Building operators can also see more about their building in real time than is probably currently available to most building operators. Not only is historical and current peak demand, ongoing demand presented in a digestible form, but they're also kind of predicting what the peak demand could be and whether a new peak demand could be set, and then giving some advice around basically a heads up to the facility operators to make sure that if they can, to take corrective action to not set a new peak. And then we're also working with the GSA on a different software platform at 2 other buildings, one in New York and one in Colorado. Very similar functionality, similar metrics, similar operation. It's called Synapse from Kinetic Buildings. And then switching gears from the General Service Administration to the Department of Energy, and hopefully something that's a little bit more in an architect's wheelhouse as opposed to HVAC, which I've talked about previously or up to this point in this presentation. We're about halfway through a demonstration project for the Department of Energy, in which we're demonstrating a package of technologies. The automated shades is maybe the most relevant. It's a automated shade technology that will, given integration with the building's operating system and lighting system, will find an optimal shade location to reduce peak demand or reduce ongoing demand of the building. So if it's hot outside and the compressors and fans are all running really hard, it might opt to drop the shades to reduce the cooling load on the building, as opposed to what might already have been programmed to keep the shades open in order to keep occupant views, or maybe even maximize lighting photo control savings. There's an interesting balance between shades and HVAC consumption and lighting consumption in an environment where the shades are automated and the lighting is controlled with photometers, daylighting controls. And we're trying to figure out kind of the optimal control strategy for a couple of commercial buildings. And then I wanted to kind of end on an example, again, from the Department of Energy. As you may have surmised, there's a big push from them to put research around grid interactive efficient buildings at the forefront. And that came to a head when they announced the winners of what they're calling the DOE Connected Communities Grant. There was about $60 billion they're going to give to 10 teams to demonstrate basically what we're talking about: smart control, sensors, and analytics, grid interactive efficient buildings across the country. We were fortunate enough to be one of those teams selected. Our project just kicking off here in the next month or so. It's going to demonstrate a variety of things, both on the HVAC and lighting side, as well as HVAC control integration, EV managed charging, and battery storage. So a lot of things that you've heard myself and the other presenters mention so far. A little bit more detail. So this year and for the next couple of years, we're going to go into 5 or 6 City of Madison municipal buildings. That's roughly 300,000 square feet, and we're going to implement energy efficiency through HVAC and lighting controls. Then we're going to use those controls platforms to demonstrate load shedding via automated demand response. The City of Madison has a pretty sizable electric vehicle fleet, and it's growing. They've recently built a new vehicle maintenance headquarters here in Madison, and we're going to implement some managed charging to hopefully spread the load of those charging vehicles across a more grid optimal scenario charging schedule, and then also do some implementation of batteries co-located with photovoltaic arrays to help spread out that duck curve problem, try to get the generation to more closely match the grid's total power demand. We're going to take what we learned in those buildings and work with our local utility here to develop a grid interactive efficient building program for their medium to large commercial and industrial customers. We're hoping to demonstrate a lot of the same technologies, just kind of scale up the number of buildings and chargers and batteries. The utility is going to implement a central management system to help optimize the usage of those GEB elements across their service territory. And then we're going to take what we learned from all those buildings and wrap it up into kind of a framework for what other entities, other organizations, other utilities could be doing to scale their own GEB programs. That'll be in kind of the 2025, 2026 timeframe. And then kind of ending, I alluded to the fact that the DOE has a strong focus on GEBs, and just wanted to call out that they published a series of reports on future research that they see as top priority. And there's a pretty lengthy report on each of several building systems, from HVAC to lighting and plug loads and envelope. And I just wanted to pull out this table from the envelope research document, which highlights a few envelope elements. I mentioned automated window attachments. The DOE thinks that has high potential for grid flexibility. And they also call out dynamic glazing, which I know there's more than just electrochromic glazing, but my mind always goes there first with dynamic glazing. And then I do not know much about thermally anisotropic materials, besides that their R value is dynamic in opaque elements such as wall insulation. Thermal storage, I usually think of that as being, in this context, as being, the word's slipping my mind right now. I'll have to come back to it. And then tunable thermal conductivity materials are very similar to thermally anisotropic materials in that, the thermal properties of the windows or the walls and the roofs are can be adjusted in real time. And I think that's it. Oh, there's a few resources that if you want to learn more, I can certainly share some links to additional information around all of these demonstrations and what the DOE and even ASHRAE, what they're doing in this space. So thanks.
Great,
And
thanks, Scott.
Back to Richard.
And we've answered some questions kind of along the way. I'm going to just ask a couple of, we've got maybe 8 minutes for questions before we take a short break, and then we have kind of our virtual happy hour and virtual tours of the Science Museum facilities. But a couple of questions for these panelists, and I'm going to, as I ask the question, I'm going to post it in the chat to everybody. But the first one is, how can projects and design teams, even though, and I just want to kind of re-emphasize, this sort of space is still very much kind of under development in research. What are the, what's the value proposition of all this, and how do you construct a business model between customer, building owner and utility is still kind of an emerging area. What technologies have value, and how do you do some of this stuff is still kind of an emerging area. So I want to just kind of re-emphasize that context, as this isn't a solved problem, or a solved space, if you will, that, oh, here it is, and integrate it in. But regardless of that, what are some things that projects and design teams can integrate GEB's thinking into projects right now?
Well, I think you don't necessarily need to put it into a GEBS context immediately. I think the reality is, to be able to have the functionality, to have the building have the functionality to be able to do those interactions. And that means, how do you have the ability to communicate with the grid? And you have to look at where the different interfaces are. So if you just look at the building itself, I think looking at utilizing smart technologies and creating intelligent buildings, that they have obviously the ability to do that provides a lot of utility benefits to the occupants anyway. But having those technologies and systems in the building then opens the way to communicate, bring the external communication. If you have the internal systems that connect, generation with usage. And I think not necessarily thinking in terms of GABs, but thinking in terms of intelligent buildings.
Yeah, great.
Yeah, I guess I just added, I think that's a fair point. Just simply having a connection to a network is the big enabling feature of all these systems. Being digital, being able to adjust control sequences is key. And then on the hardware side, I mean, and that's true across most traditional building systems like HVAC and lighting, plug loads. If it's smart and can accept a signal and be controlled, then you're most of the way there. On the hardware side, I guess, if you can consider a battery, great. If you can't, maybe do the sort of things to make your building battery ready that are, not too dissimilar from the PV side in terms of running conduit, making sure you have enough clearance in somewhere to put a battery. There's a variety of kind of battery ready design considerations that would allow you to much easier drop one into your building down the road, should you choose to do that.
Yeah. And Scott, I think that's kind of one of the, I mean, if you're doing solar ready, net zero ready, having, like, as you say, having storage ready as part of that is almost essential now, as we think going forward, because I think, I think particularly when I think, so I have solar plus batteries at my house, and there are times when I think actually the batteries probably have more value to the utility than the solar does, or some optimization between the two, as we start to think of the future value proposition.
Yeah, the same is probably true with EVs too.
Yeah.
I wish we at our building had stubbed out the trench and run it out to our parking lot so we could just drop the charger on there.
Yeah. So maybe that leads us into our next question, which is, how do all these kind of distributed energy, technologies and thinking about these things, how do they change the value proposition for building owners, occupants, and utilities and governments? So. And Andre, I don't know if you want to, yep, there you go. I don't know if you want to kind of start us off here, see how maybe the utilities thinking about this could start to change the value proposition.
Yeah, so I think from the utilities perspective, we want to be your energy supplier. We want to make sure we provide you safe, reliable power when you need it. And I don't think we have a strong desire to control loads within your facilities. That's kind of up to you, the customer, to do that. But we want to be able to provide you with information that tells you how to better manage your buildings so that it complements what's happening on the grid. So if we can send you these demand response signals and say, hey, we have a constraint right now. If you can shed load, we'll incentivize you for shedding load. Or in the future, conversely, if we have excess renewable generation, heck, we might pay you to turn something on and charge your electric vehicle during off hours or something when we have excess generation on the grid. I think that's kind of the magic of these GEBs to the utility, is that it provides a way for us to tell the customer what we need and what the energy prices are, and then the customers can respond to that automatically through the smart buildings.
Yeah, any other additions to that? So there's a question, I think, in the chat, well, a couple questions in the chat. So one is Matt said along those lines, if the grid is 100% clean, does it become purely economical? Therefore is an energy code not needed? So, I mean, I'll kick this off and maybe others can kind of come in behind here, but I think that so one of the key questions we're trying to figure out is we start to have a built environment plus grid that is meeting our climate change goals. What's the appropriate, at what scale is the most cost-effective place to put resources? So grid scale renewables, neighborhood scale renewables, some level of distributed renewables as well. And that's both from a climate change perspective, but I think also as we start to weave in resiliency considerations, grids and resiliency at what scale. So I think that is the thing that we're trying to figure out, what's the sweet spot and what's the optimized level, and also realizing that there isn't one answer to that. It's a dynamic situation in time, kind of in space, and in kind of requirements. I think with all of that, some sort of efficiency requirement will still have to be woven into the built environment space for resource planning. It's not going to be, Andre, maybe you can jump in here, but the grid's going to be planned with a certain level of efficiency and resource assumptions. And just because it's 100% renewable, we can't say, well, whatever, use it as much as you want now, because that comes with a cost of increased generation capacity and other things to take up that. So I think it's an optimization question, but I'll leave it to kind of others to jump in behind me on the answer to that.
Yeah, and I think efficiency is always going to play a key role, because we don't want to have to overbuild the system or just waste those electrons, if you will. If you can make your buildings as efficient as possible, then we end up don't have to build as many assets, and that helps keep overall electric rates down for everyone.
Yeah. And I think this is also why we see, and again, this is what in SP 2030, our cost effectiveness calculation, as renewables are increasing on the grid, our ROI is coming down because it's less cost effective to put them, it's trying to balance out that question. Should we be integrating them in the building, or are they being deployed in the on the grid? So another question we have in the chat is, could we say more about the resilience co-benefits of storage microgrids in addition to the energy efficiency, carbon, and economic benefits? So.
And that's one thing we're addressing through our Resilient Minneapolis project that we filed. The 99.9% of the time, the battery assets we intend to deploy will be there for grid purposes. Dispatch them, for whatever the grid needs, but then we'll always reserve a certain amount of backup power to provide power emergencies to those site hosts. And then by combining that with the on-site renewables, then hopefully we can run those facilities for a long duration of time, because if they have excess solar generation that can meet the needs of their building, and then the excess recharges the battery to get them through like overnight hours. So I'm not sure if that addressed your question or not.
Yeah, and I think, adding to that, and we did, I'm trying to find it right now, but and I'll post a link to it in the chat, but I mean, our first at the centers, introduction to GEBS, I don't even think we knew it was called GEBS at that point, but we started to look at integrating resilience into SB 2030 buildings by mimicking natural systems. And that started this sort of study of integrating storage into energy plus water systems and other things. And out of that work, I think the other thing that could come out of Geb's research is thinking about, as you design a building, how do you think about multiple modes of operation, where there's sort of the regular mode of operation, but if for some reason in resilience, you kind of switch over to kind of stay in
critical
place
loads.
mode, critical infrastructure
Yeah.
mode to maximize your battery storage, or like some of those facilities you're talking about in the Minneapolis pilot project, they might have kind of a resilience hub mode where it's a place where neighborhood folks might come in, in a resilience event to charge their phone batteries so they can communicate, et cetera, et cetera. So I think that's another, potential thinking in this research in the future. So
Yeah, and we are discussing that with our site hosts. What loads do you run during an emergency where you're running off of battery power? So we have we're deploying a battery storage system at a community center, and we intend to integrate with their building management system, so they know you're in microgrid mode. You only have this much state of charge in the battery left. You need to conserve power. So shut off your kiln. You're not going to hold a pottery class and run your kilns, electric kilns, if you're in this crisis mode where you're running off of battery power, for example.
Yeah, and maybe some of the benefit there might be is if you're a facility that has an emergency need, like you would have bought a diesel genset otherwise, and instead you're be able to operate with batteries and PV, then not only is that cleaner, but also you can get more value out of it. You can't run your diesel genset for a demand response event. The EPA doesn't allow it, but you can use your battery anytime you want to minimize peak demand charges and respond to demand response programs. So you're kind of killing two birds with one stone, I guess, or value stacking and getting more value out of the same system, I guess, is a better way of saying that.
great. Well, thanks everybody, and thanks for great series of panels today.